Now that we have acquired the design loops acting on the beam, next questions, you are asked to analyze the continuous beam using the moment distributions method. The question specified that the loop arrangement it will be maximum, minimum, maximum loops. Before we look into the questions, you know that when analyzing a continuous member, you will need to get the envelope shear force diagram and the bending moment diagram. This is in order for you to acquire the critical moments at different places of the continuous beam. There is no single load arrangement that can give you all the critical shear force and critical moment throughout the entire continuous member. That's why we will need to test with different loops conditions. In general, there are two types of loop set. You may use maximum loops throughout as the first type of loop arrangement, and then maximum, minimum, maximum, and so on and so forth as the second loop arrangement, and then minimum, maximum, minimum throughout as the third loop arrangement. The combinations of these three forms the loop set that can give you the critical shear force diagram and the bending moment diagram as an envelope of all three loop cases. Alternatively, you can use the loop set 1. For the loop set 1, you do not have the loop conditions of the maximum or, but you will have maximum, minimum, maximum, and minimum, maximum, minimum. On top of that, you will have two consecutive span with maximum load that progressively move along the continuous span, as demonstrated by the load arrangement 3, 4, and 5. Now, what defines the maximum and the minimum loops? Let's say we are referring to the ultimate limit state. The maximum loops shall be considered the existence of the GK and QK, while the minimum loops, there will be only QK. QK refers to the permanent loop. Whether you like it or not, it will always be there, regardless it is maximum and the minimum. As for the GK, it is variable actions, which can be there and can be not there. Now, if you assume it is the maximum load, you will have full flash of the QK. As for the minimum loads, you will assume the QK is absent. For the ultimate limit state, the factor of safety will go with the GK and QK, which are 1.35 and 1.5 respectively. Coming back to the question, theoretically, if you need to analyze a continuous member, you will have to use either loop set 1 or loop set 2. That means you have to do the moment distribution analysis if you are using the loop set 2, loop arrangement 1, loop arrangement 2, and loop arrangement 3. That means you have to do 3 times the moment distributions method. However, if you are talking about the final exam, normally a typical paper will take about 3 hours, covering the entire course. The time provided is often not sufficient for you to do the moment distributions for all 3 cases. And you need to know the principles of final exam. Every single item will only be assessed once. In terms of the assessment, there is no point for you to do the 3 loop cases in the final exam. If you can do, you can do it all. If you can't do, you cannot do any at all. Now, if the assessment intends to know whether you can do the moment distribution method, normally it will specify which loop case you're going to do. That's why the question here specify you're going to do the maximum, minimum, maximum loop case. Now that you know what is maximum loop, that means you are talking about the GK times 1.35 plus QK times 1.5. As for the minimum load, you will consider only GK times 1.35. Since the question is continuous, you may attempt the value from the previous sub-questions. For the end span, the GK is 25.7 and QK is 7.3. As for the mid-span, the GK is 16.9 and QK is 2.5. In order to get the design load, you will have GK times 1.35 plus 1.5 times QK. This represents the maximum load. As for the mid-span, that will be GK times 1.35 only. There is no QK. Now that we have settled the maximum and minimum loads, you will need to construct a table for you to work out the moment distributions method. You have 3 spans: first span, second span, and the third span. Along the beam span, there are 4 indicative points. You may label this in accordance to the grid line based on the key plane. Point 1, point 2, 3, and 4. Next, you will need to determine the stiffness of various spans. To determine the stiffness, you may use these 2 equations. If you are talking about the far end fix, you are talking about K equals to 4 EI per L. E represents the modulus of elasticity. I represents the moment of inertia, and L represents the beam span. As for the far end pin, the K it will be 3 EI per L. The K represents the stiffness of that particular stretch of beam. Let's say for a typical 3 span, this will be the case. For the continuous part, we will assume it is fixed. As for the end span, we will assume it as the pin connections. Because of that, now the end span, you will use K equals to 3 EI per L, while the intermediate span, you will use K equals to 4 EI per L. Now, for you to determine the stiffness, you require the modulus of elasticity and also moment of inertia. This is provided that the modulus of elasticity is given. Now, even the modulus of elasticity is not given in the questions, you can still get it from the Eurocode. Normally for reinforced concrete design, in the final exam, Eurocodes are given. You may refer to the table 3.1. The modulus of elasticity, you can get it, which is in accordance to the concrete grade. Let's say for these questions, the FCK is given 30. You may refer to 30 here. Your modulus of elasticity, it will be 33 gigapascal. Alternatively, you may refer to the equations for you to determine the modulus of elasticity. As for the moment of inertia, the equations for moment of inertia, it will be BH power 3 per 12. The B and H, it will be referring to the width and the height of the beam, which if accordance to the key plan, the B it will be 200 and the H it will be 450. Now in order to calculate the stiffness K, you can adopt all the values of modulus of elasticity, moment of inertia, as well as the length of the beam into the equations. Now you will need to first know the purpose of determining the stiffness. The stiffness is used for you to determine the distribution factors. You are making the relative comparisons of the stiffness between two stretches of the beam meeting at a joint. The higher the stiffness, the larger the moment the beam will be taking. Now the quantum of the moments to be taken by different members, it will be totally identical to the percentage of the stiffness of that particular stretch out of the total stiffness at the joint. Ultimately, you will see the stiffness divided by stiffness. If you adopt the equations into the stiffness equations, you will see the E and I cancelling out each other. This is provided that the entire member here has the same modulus of elasticity. In another word, the entire beam here is having the same concrete grade. As if you refer to table 3.1, the stiffness vary with the concrete grade. So when the concrete grade is constant throughout, you will know that the modulus of elasticity will be the same throughout the continuous beam. Now when you have stiffness divided by stiffness, ultimately the modulus of elasticity shall cancel out each other. Same principles goes to the moment of inertia. The moment of inertia is governed by the beam's dimension. From the key plane here, we will know that the size of the beam will be the same throughout. Again, when the stiffness is divided by the stiffness, they shall also be cancelling out each other. Knowing that they will be cancelling out each other, for simplicity, we can simply assume the E and I equals to 1. Then we do not need to compute the modulus of elasticity and the moment of inertia. It is unless that the concrete grade along the beam span varies, or the size of the beam here varies. For example, something like this. Then you have no choice. You will have to compute the actual moment of inertia. Coming back to this example, assuming E and I equals to 1, the stiffness for the end span it will be 3 per L, mid span it will be 4 per L, and another end span it will be 3 per L. The L refers to the key plane, 5.6, 6 meters and 5.6. That gives you these stiffnesses. Next, we will need to compute the distribution factors. We are talking about the distribution factors on the left hand side here. It is calculated by having the stiffness of the left hand side divided by the total stiffness of both sides. That gives you about 44.6%. Same principles apply here. You want to get the distribution factors here. Take the stiffness here divided by the total stiffness here. Since the stiffness on this side is larger than the other side, you will expect this side giving you a bigger distribution factors than the other side. Now, whatever moment that you have computed at the joint, this side will take about 55.4% and the other side will take about 44.6%. That is the functions of the distribution factor. Since the continuous beam here is symmetrical, then you know that this side will also be identical. Next, you can calculate the load acting onto the beam. You have the UDL. The first band is the maximum load. That means your design load, it will be 1.35 times 25.7 plus 1.5 times 7.3. That gives you the UDL of 45.6 kN per meter. In order to get the load, you will use this UDL multiply the length, which for the first band is 5.6 meters. That will give you the load here. You will do the same for the mid-span, only that now your QK is absent. You can calculate yourself and check with the value here. Your next step, it will be to determine the fixed end moment. This you may refer to a table. Now the case here, we will assume it is UDL throughout. Based on the structural key plan here, there is no point loads acting onto any part of the continuous beam. The load, it will be UDL throughout. Bear in mind that when we calculate the UDLs acting onto the beam, using the table 3.15, we use the coefficients, multiply the design load, and then multiply the shorter span. Theoretically, if you are referring to the British standard at 110, the calculated UDL will add something like this, where the load shall concentrate on the 3/4 of the span at the middle of the span. At least this is what is implied by the British standard at 110. However, if you use this to do the calculations, it will be slightly more complex. In this case, normally we'll simplify it. When we calculate the UDL using this, instead of assuming the loads, it will only concentrate on the middle 3/4 of the span. We will assume the same magnitude throughout the entire span. That's why when we compute the load here, we multiply the UDL with the entire span of 5.6 meters, 6 meters, and 5.6 meters. Coming back to the fixed end moment, when you have UDL throughout, so the fixed end moment when both ends are fixed, it will be WL square per 12. In the case that one end is pinned, your fixed end moment, it will be WL square per 8. In another word, you will assume this end and this end are pinned. So you will assume no fixed end moment here. Whatever moments being contributed to this end will be brought forward back to this joint here. Now this number shall be computed based on WL square per 8, based on this equation, and then this numbers is computed based on WL square per 12 under these conditions. Now it depends on the final exam papers whether this kind of tables is provided or not. In the case that the equations are not provided, it is not difficult to memorize the equations. WL squared per 8 is a typical equations for pin supported member, and WL squared per 12 is the typical equations for fixed end members. Having the fixed end moment calculated, you will expect the directions of the moments due to the fixed end. They are counteracting each others. Assuming these directions as a negative and these directions as a positive, whatever fixed end moments that you have acquired, remember to put into the proper positive and negative sign. Since the fixed end moments are different at the joint here, that means after counteracting each other, there will be balance moment. And this balance moment shall be taken by different ends of the beams based on the distribution factors, which are computed from the stiffness. The higher the stiffness, the larger the moment shall be taken. That leads to the moments taken at both ends of the beam. Let's say this 49.27 shall be calculated on basis of this multiply the balance of the moment here. As for this 61.21, it will be the distribution factors multiply the balance of the fixed end moment. Same goes to the other side. And then start the distributions process. Having the moment here, assuming this side will take half and the opposite side will take another half. Therefore, you will carry forward half of the moments to the opposite side. Same process goes here. Half of it will be carried forward. As for this end, since we assume it is the pin connections, it is not going to take any moment. Therefore, you cannot carry forward any of the moment here. And since you have no moments to be carried forward here, then you also do not have any moment here. That brings the balance moment here, and then later it will be multiplied with the distribution factors to get the moment here, and multiply the distribution factors in order to get the moment here. You will repeat the same process until the moment after the distributions become insignificant. And then what you do next, you will sum up all the moments here to get this value, sum up all the moments here to get this value. Same process applies to the other places. Since this continuous member is symmetrical at the mid-span, so whatever you calculate here, it will be totally identical on the other side. And then now your moments at the joints are given here. Again, when it is symmetrical, both sides will have the same moment.